universe is calling you. The universe is calling me. It speaks both day and night. It's full of dark and light.
Well, hello there, ladies and gentlemen, boys and girls, ghosts and apparitions and aliens of all colors, creeds, and denominations. It is I, Mark Antonio. I'm here with Tara. Hi, Tara.
Hi, how you doing?
Good, and you might recognize Amanda down there.
Hey.
We call her the Commander. Hi, Amanda. How are you?
Hi, I'm well. Nice to see everybody. It's been a while.
It has. It's so good to have you with us. I'm hoping that we'll make this a regular thing with you again. It's been my I guess my failing to connect with you properly, so I'll try to do better on that.
Okay, you heard it here first, folks.
You heard it here first. That is
if I'm ever
correct.
missing again, blame Mark first.
Yeah, well, unless it's next Sunday, in which case she's not going to be here, as she already told me.
Okay, yeah. If there's a show, I will not be here next week, but
if there's a
happy
show.
Christmas to everyone, just in case.
There you go.
Great. Very good. So I want to welcome you to Sky Tour Radio. It really isn't radio, is it? I mean, look at you can see me. You can see Tara. You can see, well, sort of see Amanda. You see the ring around her body glowing when
ring
she talks.
around Amanda.
Ring around.
I'm like
Amanda.
the sun. My aura.
We see her aura. Not sure
and
the color,
if you look
but
directly at me, much like the sun, you'll burn your eyes out. So
not true.
I have a face for radio.
Not at all. Anyway, you might think, well, where's Daryl? Daryl's actually not feeling well tonight, so he's not with us. And we send our best to him. We hope he gets better fast. So I just want to welcome you to Sky Tour Radio here on KGRADB. And I am hoping, well, thank you, Bill. That's a very nice of you to say about Daryl.
All of us, yeah.
Yeah, it's all of us, yeah. Tonight is a little special because we have a bunch of things that have happened out there in the world that are really interesting. Okay, we had the splashdown of the Artemis mission, and what was the Artemis mission? What was its goal? We're going to talk a little bit about that. And then we also have some changes with Sky Tour Livestream, which is our companion live deep sky observatory that is currently in the western desert of Arizona. To go with the Eastern Observatory that's here. If you look behind me, you can kind of see the telescope right there. That's the one for East right there. And I keep going the wrong way. Okay, that's the Eastern one right there. And it's going to be going back in the building. The trouble is the cost of wood has been so expensive during the pandemic, and it's just starting to come down. Once we get that, we're going to get it back and build that building again. We outgrew the dome we had. And it was with a heavy heart that I sold it to a guy in Long Island who was making a great use of it. And so it's really, domes like that are not meant for automation, and we need automation. Those are meant for being in the dome. And many of you know with Sky Tour Livestream, when we first started doing this Deep Sky Observatory, I was out there in the middle of freezing cold. Amanda remembers. She was with us all.
Socks.
Thermal socks. I had electric
feel
socks
your
at
toes.
one point.
Oh my gosh. No way. There's no way.
Yeah. And I was sitting there going, and this is Measure 42. This is the Orion Nebula.
Well, that was half the reason I was invited to join you, because you couldn't look at YouTube because the light from the screen would take away your night vision. And you needed to actually step outside the dome from time to time and physically look up at the sky to position things. Like,
she is
we've
so right.
come a long way. And,
we've come a long way.
Yeah.
Now we have all sky cameras sitting outside the telescope out in Arizona, and we show the whole sky at once, so we can see what's going on out there. And we have we run it all the way from Connecticut, which is 2,500 miles away from Terra right now, she's an hour away from the observatory, and she has to drive west to get to it out in the desert.
And you're looking at things light years away, so when you're talking miles, it doesn't seem that far.
It doesn't seem that. In fact, you're right. It's in fact it's no distance at all. It's no distance at all. You're right. So we've made some changes to Skytour Livestream of late. We have upgraded our system out there. We had it tested, fixed, reconfigured to help us get the best out of it. We added some systems to it that allow us to monitor its temperature, monitor the focus of the telescopes out there. And we are about to add another telescope.
Yay!
And it looks, yes, that's right. It looks like it's going to go very possibly in another building, in another part of the state.
That's awesome.
In fact, this site we're at now is very dark. If you can imagine there's a darker site, well, that's what we're looking at now. So it's possible. I'll keep you posted on that. But the idea is that, you have two of them working together at the same time. That allows you to do some interesting things between the two telescopes that are about 150 miles apart or so. It gives you some capabilities that might have eluded us up to now. So, and I know I'm being cryptic about that, but I will bring that back as soon as I bring my camera back into center. There we go. Okay. I know I'm being cryptic about that, but I will continue to be cryptic until we actually, until we actually get moving on it. That said, and for people that don't know what Skytour Livestream is, well, Skytour Livestream is a clear night journey into the depths of deep space. We show you clusters and nebulae, galaxies, the locations where stars are forming and potentially life is beginning in some of these dark nebulae. For instance, places like this. Okay, this is called the Iris Nebula. This Iris Nebula, these dark clouds of dust are very, very chilly. They are down near, down in just a few degrees Kelvin. Now, the Kelvin scale, I always talk about Kelvin. And what is Kelvin? Kelvin is a scale, a temperature scale. As an example, here's a comparison, okay? And why do we have Kelvin? Well, if you look at that one on the left, it says Fahrenheit, right? Fahrenheit right here. Fahrenheit, that's one that's based on water. It's based on the boiling point of water. Celsius, just past it, is also based on water. We needed something that was based on no substance, but had an absolute scale. And that's what Kelvin is. All right. Absolute zero is minus 460 Fahrenheit or minus 273 Celsius. Right. And you can't have a negative Kelvin value. It's zero or it's positive. Okay. So the cosmic microwave background among the coldest areas of space are literally about 2.5 to 3 Kelvin. And they're not degrees Kelvin. It's Kelvin. That's the name. That's the scale. It's Kelvins. Okay. Degrees, you replace the word degrees with, say, Kelvin. Okay. That's how it works. So this is how the Kelvin scale works. And this is what we use in astronomy, is that Kelvin scale. We don't use Fahrenheit. We don't use Celsius much, but we use Kelvin a lot. So you can see that, okay, the moon at its coldest here, you can see on the left side there, the moon at its coldest down there. That right there says it's minus 280 degrees Fahrenheit at its coldest. Now you might think, well, why wouldn't it be absolute zero at its coldest? Why wouldn't it be down to 460 degrees below zero? Well, I can share why that's the case. Okay, then next to it, you see that coldest area corresponds to minus 173 Celsius. It used to be called centigrade, remember? And that's, of course, 100 Kelvin. Okay, now the reason the moon is only minus 280 and not colder is because of the fact that the moon has some internal heat as well, but it also has a crust and soil. And that soil does absorb radiation from the sun. And within the soil, within that soil, it's going to spread out and radiate outwards. So wherever the sun's hitting the moon, it's going to be warmed down to a certain depth. Okay. And that means it's going to average out to a temperature that is roughly minus 280 Fahrenheit. Okay. Or 100 Kelvin. So that's why the moon doesn't ever really get colder than that. And people say, well, what about the dark side of the moon? Well, again, the dark side of the moon is the light side of the moon when it's facing the other way from us. The moon is going around the Earth like this with its same face facing us. But when it's a new moon and we just have a dark moon that we're looking at the shadowed side of the moon in its entirety because it's on the same side as the sun is, well, then that shadowed face we're seeing is going to be colder than the other side, which is now in full light. So from the other side of the moon, it's a full moon as seen from the sun. So the moon has light on it at all times. As it's going around the Earth, it always has light on it. The only time are in those rare instances where the moon passes into our shadow and we get the lunar eclipse, right? We just had a really interesting situation with the moon. We had a lunar eclipse lately, and we streamed it. We saw some pretty interesting, changes in color on the moon. It was nice. But then the other night, just December 7th, in fact, we had a lunar occultation where the moon was actually passing in front of Mars, and we caught it, and it's really neat. And I'm just gonna, while we're talking, I'm gonna actually try and bring that up. I don't believe I forgot to bring that up, and I did, so it's my fault. Blame me. Don't blame her. Don't blame her. It's me. Okay.
It's all good. It's all good.
It is all good.
Yeah.
Yeah. So I'm going to show you, though, real quick, what we saw, because it was actually kind of cool.
I was going to say, if you have it in our Sky Tour live stream on Facebook, I can pull it there.
Yeah, you know what, Amanda? That's another thing that's changed, but I don't think you were. Maybe you were. We now have skytourlive.com and skytourlive.org, and that's the portal into everything we do. So that is a portal to our Facebook site, to our Twitter, to and to the database where all these pictures are kept as well. So, but you're right.
Oh, well, I can get it there. Yeah.
Yeah, I should have done that. I did not. What I'm going to do is I'm going to just quickly share my screen to show people. All right, what happened.
Awesome.
So this is the moon, the full moon, and when we looked at the moon the other night, we saw this. Now, this is just after it emerged. This is Mars emerging. It came out right about here, and it went in right about here. So
cool.
It took just about an hour to go across, and with the observatory, it was such that the observatory walls were too high, and we couldn't catch the moon entry where Mars was going behind the moon, but we could catch the exit. And we watched the exit live. I didn't bother taking any pictures of it because I didn't want to mess it up. And I took pictures just a couple minutes after. So here is rusty, dusty Mars emerging from this side of the moon. And if we go back, I can take us back to one more directory. And this was before that moment. And you can see here that you'll see Mars is actually even closer. Because this is as it had just emerged. See that? So it was kind of cool to see that. And you can actually see detail on the Martian surface here if you zoom in. But again, this telescope, the way our telescope, this is the field of view of our telescope. It is literally 4 full moons across and 3 full moons tall.
It's huge.
Mars is just a tiny little, little tiny disk that is not going to be visible, very well. All right. And so the next telescope is going to allow us to actually see detail on Mars very, very clearly. And we'll also be able to see detail on the moon in a way that we have not been able to. So the two telescopes will be different, but they'll be able to do the same types of things, So there you go. That was that was Mars being passed in front of by the moon. It went in over here and it came out over here.
It looks
Very
rusty.
cool.
Yeah.
It is. Yeah. Yeah. Mars is interesting, and when I was a kid and I know I was 9 when I said I'm going to be an astronomer, and that's what I did. It never changed. So I kind of was boring like that. I said, I'm never going to change. I don't want to do anything else. No, Mom, I'm not going to be a doctor. I'm going to be an astronomer, because astronomers get so much cool information. They don't get so much cool money, however. So, but I'm very, very happy with what we've done. So now, as an example, when you look at this, you look at how Mars turned red, for instance. I read books about it, and back then they had an idea. They had spectral analysis back then. They could figure out that Mars was kind of rusty. So like, a whole planet rusting? How could that happen? Well, it turns out that you have to look at the whole history of Mars to understand that. And Tara, I think you've asked some questions about this in the past, about Mars and the red coloring on Mars. But I'm not asking you, I don't want to put you on the spot like you have to go hunt them down. That's not what I was doing.
No.
But I think you did.
But it's all oxygen related, isn't it? And
yes, it is. And that's what's very interesting. Now, she's absolutely 100% right, that woman over there. Okay. Because Mars used to have a much thicker atmosphere. Okay. And that atmosphere, little by little, as the Martian magnetic field began to die away, the ultraviolet energy from the sun was no longer being stopped by the magnetic field like is happening here. The high-powered solar flux, the particles, the high-energy solar wind coming from the sun is stopped by the magnetic field and trapped by the magnetic field. This gives rise to what we call the Van Allen radiation belts. See, the two are one and the same. It's just that the magnetic fields are effectively made visible, if you will, by these charged particles of high energy that have come from the sun. These are protons and electrons streaming to us at high speed from the sun. And Mars was doing that too. We are protected from the ultraviolet, which to the most part, because when we go outside, we can lay on a beach and not get deadly skin cancer immediately. Okay, it takes a number of years to get deadly skin cancer, but that shows you that some of the ultraviolet gets to us on the planet. Right. So Mars, on the other hand, as Tara was saying, used to have a lot of water, which of course is H2O, oxygen.
Wow. And
the H2 and the O, can be disassembled as a molecule by ultraviolet radiation. It's called photodissociation. So when Mars would have water that would evaporate, because Mars used to have a thicker atmosphere to go with this magnetic field that it had, and this thicker atmosphere would also generate clouds, and there'd be moisture in the air from lakes of standing water that were on Mars several billion years ago. And when that happened, the Martian atmosphere, lakes would evaporate, and now you have water vapor in the air, but now you have the ultraviolet energy striking those molecules of water vapor and pulling away the oxygen from the hydrogen, which gets lost to space. Bye. So long. And the oxygen now is sitting there going, I don't know what to do. So it dives down into the ground, and it ended up bonding with compounds in the ground. Many of the compounds were iron, because Mars has an iron, regolith or soil, right? And so it made a lot of compounds that were called hematite, also rust. All right. So, and they're reddish. So that's why Mars turned red long term, because all the water went into the ground. All the oxygen went into the ground and ended up bonding with the iron compounds. When it bonds with iron, you get 2 iron atoms, and 3 oxygen atoms. You get Fe2. The 2 is 2 iron, O3, and 3 oxygen atoms that are attached to that iron. And now you have this compound we call rust. So that's what happened at Mars. And so when you look at Mars now, it's a shade of this beautiful red. It's the beautiful red planet. Yeah, but it's red everywhere. Except when you brush away the dust on the surface, you can see some of the original soils of Mars, and they're actually dark brown. And that's interesting, right? We've seen that. I mean, when you look on Mars, you see dark patches sometimes, depending on the time of year. You see dark swaths. Okay, there's one called Syrtis Major, and it's like a dark black area on Mars that you can see in the telescope. Well, that's the underlying non-rusted or partially rusted material below that rusty layer. All right.
Was something blow it away? I mean, how is that exposed?
Yeah, that's true. I mean, there are seasonal winds and changes in the climate that do blow some of that dust away. We also have global dust storms on Mars, which is something we don't have here. Now, Mars is smaller. Okay, Mars is smaller, and it only has 40% of the gravity of our planet. But the thing is, when dust gets in the air, the dust on Mars is literally the consistency of talcum powder. And you know what happens with talcum powder? If you blow some, it's all over the place. It's on everything. Anything you dust, the mirror, look at that. The counter, look at that. I didn't think there was any there, but there is. You wipe it, it's on there. Same thing, talcum powder, consistency in a soil will go planet-wide. Gets way up in the stratosphere and goes all the way around the planet globally.
Oh, that's incredible.
Yeah. And so that's that little red dot that we saw here. Right there, our little red dot, So in time, I think that we'll actually be able to check out Mars with telescope number 3. Okay, that's Sky Tour 2 is the one in Arizona. Sky Tour 1 is behind me, and Sky Tour 3 will be the third telescope. All right, so we will actually be able to have, you know what it means for me, right?
More work?
Yes.
You're never going to sleep.
Amanda's right. More work, and what else? I won't have any reason not to stream because somewhere of those 3 sites it's going to be clear.
Right. How cool. How cool.
Yeah.
Nice.
So I'll end up living a true third shift, I'm sure. But I will say this. I'm also looking longer term to put a system in the southern hemisphere.
Ooh, that would be so wonderful.
That would be huge.
Down in Australia. That would really be something. And,
I volunteer to go run tech issues for you.
I think you're going to have to go.
Okay, yeah, I might have to.
Well, I hear the spiders are bigger than the telescope you're setting up. So, Tara, best of luck. Send a postcard.
Well,
I'll do that.
Actually, the last maintenance where we had to do the maintenance, Tara has a story that I want her to tell.
Oh, God.
Oh my gosh, we were in there and my goodness, we were taking the telescope apart and had been moving boxes around, and Marianne spotted it, but she called it an She was pointing, going but it was a huge tarantula that was under the keyboard and
my
the
God.
table. It was beautiful, but totally unexpected. So he got relocated to outside of the building, which is great. We didn't harm him in any way, but it was great. There's lots of critters everywhere, Amanda. So.
Yeah, well, yeah. You can keep them. I mean, I have a heater. I don't need the sun.
Tarantulas are actually very, very docile, and they let it crawl all over their hands and on their arms while they were relocating it. It wasn't really a problem. They don't bite unless really, really provoked. You really gotta want to get bit.
Even though he's not part of the show where you can hear him and he's on mute, I swear I hear our producer screaming right now. I feel
true.
the same way, Bill. Me too.
Bill, can you join us for a second?
That's funny.
Oh, he's probably still squeaming.
Yeah, I know. He probably is. I want to say hi. Marianne Robb is with us. She's out there looking in and listening.
Hi, Marianne.
Hi,
And we got
Marianne.
a number of people. A lot of people that are, Sky Tour live stream folks are here, which is so nice to see them all. Marianne, of course, is the one who was screaming like a little girl when the tarantula was found. And she ran, and she was on the phone with me trying to show me what was going on and streaming it so I could see what's going on with the telescope to tell them what to do, because I was 2,500 miles away. And all of a sudden, this is happening. The phone is going all over the place, and I'm hearing her scream like, "What happened? What happened? You okay? What happened? Did the meteor strike? What happened?" She goes, "No, wait, there's something in there. Yeah, there's Dale and Tara, and something else. What? I don't know. What do you mean you don't know? What'd you run from? Nothing." and it turned
Yeah,
out it was this big spider.
And for those that don't know, Mark's talking big in another state, but Marianne's a retired police officer, and we are still waiting for a live stream tasing of Mark. So
that's not gonna
keep
happen.
talking, screaming like a
No.
little girl. Yeah, running away from nothing. All right, Marianne, I hope you're taking notes.
Okay,
She's ready for the right timing. So
I think
Didn't you get bitten by a spider not too long ago when you were down there, Mark?
No.
I thought you got bitten by something. I know you had heat exhaustion, heat stroke, but
Yeah, because I was
I thought you
stupid.
got bitten by something. I know Marianne thought she got bitten by something.
yeah.
Yeah,
puffed up, but-
her elbow was big, gigantic, bulbous
Yeah.
thing. It looked like a giant second
whole
head.
arm.
It was a head growing off her elbow.
Yeah, I thought someone got bit,
Vestigial
but
twin.
Yeah, it was a vestigial twin trying to get out. Let me out! No, I didn't get bit. I just got the heat stroke. And that happened because I was
the
trying to
dehydration.
fill in trenches and thought, well, hey, you know what? I don't need to drink any of this. I feel fine. Yeah, right. You pinch your skin and it stays. It's like, oh, that's cute. That's interesting.
Mhm.
And it was Marianne who basically said later that night at 11 p.m., I'm taking you to the hospital. I don't need to go to the hospital. Stop it. Come on, you're going. And it's like, drag me. Ow. Just like my mother pulling me out by my ears to go to the car to get into there and go to the medical center. And they took one look at me and they started pumping fluid into me. And the next thing I know, I took 3 1-liter bags, one after another. And I was like, wow, I guess that was I need a lot
You
of
were
hydration,
thirsty.
huh?
Yes.
My
So
body was screaming for water.
for
You don't
everyone
realize it.
listening and watching, please realize that these people are sacrificing life and limb to bring you these incredible pictures and images, and a lot of the times they take requests if there's something specific you want to see. So they're
Oh, yeah.
putting their
Mhm.
bodies on the line morning, noon, and night, and all for free and all for you. So
All for the cause. It's all worth
subscribe and tell a friend.
it.
Yeah. Sky Tour live stream. In fact, I thought I had a little banner for that, but I don't seem to have it now. I had it up here. I don't know where it went, but we're actually available now. If you want to find us, if you want to come to everything we do, see our portal to get to us, it's skytourlive.com. And now skytourlive.org, because as of now, thanks to Tara and to Marianne and my minimal
And
efforts,
you? Yes.
the Sky Tour live stream is now a 501c3 not-for-profit organization.
Yay!
I think that's worth celebrating.
Yeah.
That's awesome.
So now-
Great.
Anybody that wants to donate to us or whatever to help us get equipment and stuff, all those donations are a tax write-off, and you can claim it all without any problems whatsoever. And I'm really, really pleased that this happened, because it was a long time coming.
Yeah.
It's the closest I think I've come with SkyTour Livestream personally to make this an actual going concern that will actually be able to bring you stuff and bring you the night sky in a way that you've never seen it before. I've looked online. There is no one doing what we do. Absolutely no one. I've looked. I'm being fair about it too. There are people that stream once in a while. There are people that do live streams of, like, the sky and their house and the lake and, meteor showers, like Bill Skywatcher, our producer. That guy is an unceasingly amazing human being who will go out there and just do these beautiful meteor streams showing you the night sky. And I'm sitting there going, wow, these are beautiful. And I'm saying, on one hand, I would like to be able to do a stream like that. And on the other hand, I'd rather come here and just watch Bill. He does it so well. So, we all have our place, right? We have P&K Space Imaging, which does the moon. And they do the moon especially well. And the planets. And, we hadn't had the capability with this telescope to do the planets or the moon very well, because our telescope was a wide field, as I showed you, 4 full moons across, 3 full moons tall. So that's our field of view. So we do gigantic nebulae and show people things that are just astonishing, like this. This
Ooh.
this is 2 frames. Okay, it is six moons tall, okay, and 4 moons across. All right, and it's called the Spaghetti Nebula. So for those that like Italian food, there you go.
I do.
Okay, this is a supernova remnant left over when a star blew up, and so we take pictures of that, and you see it. You see it developing right before your eyes. So yeah, it's just amazing how that all works. I'm just so happy with that. But in any case, as a 501c3 now, you can go to skytourlive.org, and it'll take you to our entry portal where you can then go to SkyTour Livestream on YouTube, see a gallery, learn about us, see everything we do. Right, skytourlive.org. I feel like a late night. If you act now, we'll send you Slim Whitman's greatest hits.
The .org reroutes me to .com, but
yeah, it does. And so yeah, we have the .org as well, and that just takes you to the .com as well. It's a redirect. It's called.
And it's awesome that it's there. This is incredible. The changes that have been made just in the last year or so.
Well, I'm looking at the person, okay, that helped make a lot of those changes. Okay, I'm going to tell you right now, folks. This whole observatory thing started with an idea I had. And it came to fruition because of Tara, because of Marianne, because of Daryl, and because of Amanda, and because of people that stood by us and believed in this dream, and you have no idea how humbling that is. I could have an ego and be arrogant sometimes because I can be a jerk. Everybody can. You should see Tara when she's arrogant.
It's part of our shared humanity.
I've never seen Tara arrogant. What am I talking about? No. But it does take you down a notch to see all these people that will step out and help you, knowing full well that you're not paying them to help you. They just want to do it because it's cool and because they believe in it.
It's a privilege.
You see, that's what I'm talking about right there. Privilege.
It is.
What kind of privilege is that?
Well, no. Yeah. I don't have a telescope. I can't go out and set one up myself. So to have this opportunity to have this portal and to access to these images, it's a privilege. It's how I look at it.
Yeah, so. There we go. Amanda, you must have done that. Thank you so much.
So good.
Thank you. What a sweet thing. I was trying to. I had that banner somewhere and I can't remember. Oh, I know where it is now. It's under banners.
I just created that folder. I don't know where it went. We had one. I don't know where it went.
I did. So. Yeah. Okay. Yeah, that's all right. That's fine.
And our very first banner, skytourlive.com. Yeah.
Skytourlive.com. Yeah. Or skytourlive.org. Either one. Mm-hmm. Thank you, Amanda. And so I'll tell you, we are also on the cusp of being able to do some real astronomical work too with these telescopes. When you have more than one telescope, you can do work between the two that might be very, very helpful, especially if you have like a 150 mile separation. You can actually do some really interesting stuff. Okay?
3D?
Yes.
Ooh.
That's right. Not when it comes to astronomical objects, that are far away, like the Cave Nebula here, for instance. Okay, that's way too far away for that. But when it comes to like satellites, we'll be able to see satellites traveling through the sky against slightly different stars because we're moving down the Earth a little bit. So we'll be able to triangulate their height, altitude, speed, distance, all that stuff.
That's fun.
Yeah, that'd be kind of cool, And we might, that distance may be a little small, but we might be able to do a 3D moon with that kind of distance. If not, we'll take the East Coast telescope here, all right there, and we'll take the West Coast, one of the two, when they're set up, the current one and this one, and we'll be able to take pictures of the moon simultaneously, and you'll physically see a difference from what you're looking at. Okay, a little bit, a tiny bit of difference, and that's the thing that will be interesting. And from that tiny bit of difference, it's a look angle difference. You're looking at it from Arizona like this, and then from Connecticut, you're going to see it like that. It's going to be a little bit tilted because you're going to be looking at it from a little bit on the side. You put those two together in a 3D image, and you'll see the roundness of the moon from across the United States, which is really kind of cool.
Oh,
yeah, I think that's pretty cool.
That is cool.
Yeah, it is.
Is that parallax or is no? Or...
Well, actually, there will be a parallax angle that you can calculate, yes. And basically, you're looking at the moon. Now, these are simultaneous views, okay? So you're going to be able to get a 3D image of the moon. But if you actually, say, look at one side of the Earth's orbit and take a picture of distant stars and then some close by stars, then go to the other side of the Earth's orbit and take the same picture of those same stars. Those stars that are closer will look like they've shifted against the background of farther stars. And that gives you what's called the parallax angle. That's what I did as an astronomer. I worked in the parallax program, and we calculated the distances to nearby stars. And with better technology and other telescopes, we will end up, we ended up being able to see further out using parallax and get more accurate data, So we can see out to about 300 light years and get distances out to 300 light years. Wow. As a kid, I used to make a model of the solar neighborhood. I actually made a square on top, a square piece of acrylic on top, a square piece of acrylic on the bottom, and I put black threads that I put beads on. And the sun was in the middle. And so in the middle was the sun, and then I had these square beads all at different distances and so forth from the sun. And as you turned it around, because it had a post up the middle, right? You actually turn it around. You can actually you could see the 3D rotation of the nearby solar neighborhood. Now we do it with a computer. It's like 12 seconds. Oh, there we go. Okay, now got any pizza? I mean, that's all over, right? But this took me like a week to build this thing. And I just stared at it and loved it. I put the black light on it because I made them black light, things. So it was really like, wow. I mean, it looks like a cool scan. I built a fake window so I could look in and pretend I was looking through a spaceship,
Cool.
Yeah, so it's neat stuff.
It's imaginations.
Yeah. Mm-hmm. So, tonight, I know that, I mentioned we're going to be talking about stars like our sun and so forth. And we will. In fact, we're going to get to that, certainly. And I just wanted to make sure everybody understood that the news about Skytour livestream. And before we go into that, I do want to also mention the Artemis mission. The Artemis mission just concluded, and it was a brilliant success. What was Artemis? Artemis was a spacecraft system that was launched into space that then went to the moon, orbited the moon, and basically came back to Earth. Doesn't sound like a whole lot, right? But you have to understand that we didn't have the technology to do this anymore. After the Apollo era, the Saturn V rocket and all of the moon rocket technology was lost to time. Those people retired, they died. And although the specifications were still around, this was really old 60s technology. And we couldn't risk, nor could we even make the same technology that was available in the 60s. We didn't have that anymore. We didn't have the systems, didn't have the machinery, didn't have the infrastructure to actually build these engines the same way that they were.
I still don't understand that.
Yeah.
I really, really don't. Can you give me a logical explanation of how everyone just forgets a technology? How to build
It wasn't a forget, Amanda, but that's a very good question. It wasn't that we forgot. It was just that we moved on to other priorities. We started building the International Space Station. That didn't need moon rockets. That just needed the ability to get into Earth orbit. And so that's when the focus came. The shuttle, and by the way, the shuttle concept was like 30 or 40 years old when it actually was put into service, the concept. So it's been around for a long time, and not around as a technology, but around on the drawing board. And so they said, okay, we're going to be doing a lot of Earth orbit stuff. So we're going to focus on doing Earth orbit stuff. And so the scientists that worked on the moon missions and so forth retired, and as I said, died. So that expertise, how to handle this particular computer, at the time, very primitive machinery, was lost. And they weren't teaching it anymore because they figured, well, we're going to have to give that a shot in the arm and reinvent it, because it's old technology. It was very inefficient, but we somehow made it to the moon, And so with the advent of the space shuttle and the building of the International Space Station, our attention focused to near Earth. And we started doing near Earth missions, bring the Hubble Space Telescope into space, have space shuttle missions go dock with the ISS, do missions like that, and do repair missions, satellite deployments, and so forth. Well, once you do that for basically a couple of decades, and you're in that mindset, the technology to make those earlier things is lost to time because they know it's old stuff. It's like saying, we're going to go back and refurbish this Model T because we want to go on this trip. Well, the Model T is not as efficient. The Model T isn't going to get you as far. The Model T requires too much energy to get us there. We can do it much better nowadays. So we're going to scrap the Model T entirely and build a new car. So that's effectively what we did.
But we didn't build a new car.
No, we built a new space system. It was the space shuttle at the time.
I love that. I got to agree. See, but I mean, even your explanation, which is great, doesn't it sound a little backwards? Like, why would we try to get to the moon first and then it just in Earth orbit? Like,
Well,
wouldn't that be like gradual? Then, okay, we made it this far. Let's push it a little further to the moon. Let's try to get to Mars. Like, well, I don't know.
You know,
and there. What about their trips to Mercury and Venus? Even though like the Venus craft melted, but
they knew it would. And that was the Venera. That was a Russian Venera.
But was that all before the ISS? Like, why are we going so far out before? Like, that seems backwards. And then,
well, remember, there was concurrent missions, right? I mean, the mission to Pluto, okay, the New Horizons spacecraft, that was on a journey of 15 years to get there. And when it got there, it showed us things that we could never have imagined. And then New Horizons had its day in the sun when all these images came in. And then it went out and we had it again. We had another day in the sun with Ultima Thule, which is that amazing double pancake asteroid that was...
snowman?
That's exactly like the snowman shape. It was orbiting in space, linked together like that. That was Ultima Thule that it passed. And so it had another day in the sun, which is very rare for a space probe, And we sent the Cassini mission to Saturn, where it deployed a lander, the Huygens lander, which actually landed on the surface of Titan, froze after a few minutes, but got a photo of the surface and sent back data on the Titanian environment and surface. So we're exploring the solar system, not to mention all the launches to Mars. Most countries that launched to Mars failed. We're the only ones that actually succeeded more often than not. We lost one or two, but all the rest have succeeded with tremendous success. When
you say we, you mean America?
Yeah. America, yeah. Most of the other launches from other countries failed. And why? I don't know. Because the weird thing is in science, we tend to share among scientists. Scientists share information. They don't hide it, So why they failed, I don't know. It could have been because their manufacturing capability wasn't as good as ours. We do have a tremendous ability to build spacecraft. I mean, Jet Propulsion Laboratory people, from the science end of things, those people are outrageously good at what they do. The NASA scientists and people are outrageously good at what they do, in spite of the fact that they're a government agency and everybody hates government agencies. Okay. But they're good at it. Okay. They're good at what they do. Yes, they've got a lot of red tape. Elon Musk doesn't see red tape. That's why he has all these launch failures and then claps afterwards. Oh, that was cool. Yeah, it blew up, but it was a cool blow up. It was a cool explosion. There were no people on board. He would never do that ever.
Yeah, and it's his money. He doesn't have to answer to anyone. So I mean,
it's like you have to fall to learn to walk.
That's right. That's right. Yeah. And speaking briefly of Musk, I mean, he did put up the Starlink satellite. Starlink is an amazing internet availability for the world. And when you look at it and say, well, astronomers hate it because it means that you're going to get satellite trails for all your images, and we do. You see them as diagonal streaks that go by fairly quickly in your images. But then again,
yeah, I was gonna say you weren't too keen on that.
I wasn't, but now we're using Starlink at the observatory, and so now Skytour Livestream is brought to you courtesy of Starlink.
Yeah.
So I
You
can't
just
complain
never know.
too much. I ain't going to bite the hand that feeds me,
Oh,
Not a good idea.
I think he's a riot.
I do too.
Yeah.
I think he's amazing. So honestly, when you look at all the capability we have and all the things that we do now, and you look at the traveling to the moon is a stepping stone. And the reason we went to the moon in the first place wasn't because we weren't trying to focus on getting into Earth orbit. We did it because it was a race with Russia. Plain and simple. It was called the space race. And John F. Kennedy said, that before this decade is out, we're going to land a man on the moon and bring him safely home again. And we did it. So that was a space race. And after we got there, we went a few more times up to Apollo 17. And then the race was over. The funding dried up because the moon wasn't so exciting anymore to the general population. The people that were funding NASA didn't think it was worthwhile anymore. Mm-hmm. So it really was a bad situation. I personally love the Apollo missions. And if you go on the Lunar Reconnaissance Orbiter Quick Map, that's LRO Quick Map, you can dive in and see all the Apollo landing sites, zoom in, see the trails left by the rovers, tracks by the astronauts sometimes, and you can see the experiments on the surface. The lunar descent modules are right there. So if anyone tells you we didn't go to the moon, just slap them around and tell them to go to the LRO Quick Map, and tell them I sent them. You tell them I sent you. So in any case, so that's a really cool thing, so the world has changed, obviously, with the landing of Artemis safely. It signals and heralds in a new era of space capability and technology. And there's some imagery out there showing the view from the Artemis window as if you're an astronaut.
Cool.
So that's fun to see. I saw some of that today. Really neat. So the world, the universe is opening up to us little by little, and eventually we're going to get to Mars, and that's not going to be easy. That's going to be hard, and so we'll see what it takes for us to get there. We'll see. And we're taking a break on the hour, right?
About 3 minutes too, I believe.
Okay, so just interrupt me when you're ready.
If Bill doesn't tell me anything different, then we're taking a break at 3 minutes too.
Sounds good.
Yeah, as you folks can see, I'm consumed with just getting stuff out and talking and sharing stuff.
Thank goodness.
And I sometimes don't have the proper focus. I guess I'm an absent-minded kind of guy in a way. So I don't quite remember sometimes, and I have to take a break. But it's all right. Not a problem. So
I'll
moving
give
forward,
you a break. We have, speaking of Artemis, we have a few Sailor Moon fans in the audience.
Sailor Moon.
Daryl must have been talking about Usagi, the rabbit on the moon. So just for people that were kind of wondering what we were talking about, sometimes you can see the outline of a rabbit making chai. And we were talking about Usagi being the name of Sailor Moon. And Donald, I'm just teasing. I know you're, you know what you're talking about, but he was trying to educate me on Sailor Moon. So I just wanted to throw that up, throw in a little plug. I know all about
That's
Sailor
you.
Moon. That is me. Yeah.
That's you.
Usagi, yeah, she's
How
the
cute.
princess of the moon, yeah, and that's where it comes from. Are the little rabbits on the moon?
That's
I
cool.
see that. The other night when Daryl was talking about that, no, put that back up. The other night when Daryl was talking about that, I saw the rabbit in the upper left, the yellow one.
Mm-hmm.
I could kind of see that, but see, it's sort of hunched over and bent over, and it didn't look like a rabbit to me. It looked like it was sort of all bunched up. So
I think different cultures see different things too.
Yeah.
Like the Japanese one is more like the bottom right, the rabbit making chai. Right. And then in some other pictures, I mean, I just grabbed this one because I had a whole bunch of them, but you can see lots. There's like a little pestle and mortar, you know, but not in all the images. So, and I'm sure people saw things other than rabbits too. Cheese, a man, you know, all sorts of things. And buildings, castles, pyramids.
I see a dog jumping around.
Yeah, exactly. So I mean, but that's the Sailor Moon lore, and her cat was named Artemis, and Artemis just came home today. So synchronicity and yeah. Well, Mark needed a minute, so I figured I'd dumb down the show for a second. This is what I bring. Too much science. Yeah,
that's the coolest thing. It's so cool. Yeah, because honestly, you know, I often. You know, go on, and you know, I get technical sometimes, and people go, "Okay, I'm gonna sleep through this." Okay, I get it, right? So I don't mind the back and forth, the interaction. I absolutely love it. Actually, I think it's very important to the show that people get to hear more than just my blathering on about something.
Well, you know? But before there was your science, there were my stories. You know, people seeing that's what the zodiacs are. That's what constellations are. That's, you know, that's right. I mean, you know, Mars being Aries and Venus is Aphrodite. There's mythology, there's stories in every culture. And then as we realized, okay, well, maybe the thunder isn't Zeus being mad at us. Maybe, you know, maybe there's something more to it. Maybe, you know.
Yeah.
Maybe we won't fall off the edge of the earth, like, you know, just maybe little. Maybe we go around the sun, and you know.
Yeah. And I just want to address something too. You know, that in the chat, there's people talking about going to Mars, and some people said that, you know, well, Richard Dolan claims going to Mars is a been there, done that kind of thing. Yeah, I'm not on that. I'm not in that group. I don't believe that's true. I don't think that it's a been there, done that. I think that all those stories were just made by and spouted by people who just were looking to make a profit. Richard's a friend of mine, and that's not what he's doing here. But I do believe that the people that claim they've been to the Mars and so forth are literally lying. All right, and I'll say that publicly. And you know, there's no reason to expect, and there's no technology in place that would not have gone unleaked. All right. It would have been leaked. We would have known about this years ago if this was something in place. You know, people saying, well, there's these teleportation rooms. No, there's not. Okay. Stop making up crap. Okay. It's really a bunch of baloney. And I know that there are things that we don't understand out there. Okay. But I don't believe that there is a technology so advanced on this planet that we wouldn't have any inkling or clue that it's there. I think we would have known by now. I really do. And it would have come out. So I just don't think that that's true. So I appreciate when someone brings that up and says, well, hey, you know, so-and-so claims this. That's good. We'll address it, you know. You know, people do their own research, and it depends on the quality of the information they get. And then it comes down to, in the end, well, you either believe or you don't believe. You know, if you don't have the data to look at yourself, then you can either believe or don't believe. Well, I don't have the data to look at myself, and so I choose not to believe it because I don't see how scientifically it would make any sense if we for this process to be available. You know, the closest we've ever gotten to teleportation, for instance, is by an understanding of quantum entanglement. Now, quantum entanglement, as far as we know to this point, is something that is being investigated in quantum physics labs and in particle accelerators. And, you know, really it comes down to this. If you have a material and you take a piece of that object, you take apart the object. This is very, very simplified and not even accurate. But if you, it's accurate enough to get the idea. You take this piece of this object A and you put it in laboratory A. You take this piece of object A, and you put it in laboratory B over here. This object here, you measure the electron spin of the component atoms. And if the electron spin is up, you know that the spin of this one is down. You don't even have to measure it. And if this one is up, you know this one is down. You don't even have to measure it. If you change this one's spin, this is the thing that's important. If you change this one's spin to down from up, okay, then this one changes to up. And the distances are immaterial. It doesn't matter how far away they are. So that's sort of a kind of a nutshell, and there's all kinds of things wrong with that analogy, but keep in mind that the bottom line is that it appears, well, as Einstein called it, to be spooky action at a distance, where they don't really understand why the electrons of this substance will respond in the same operation, in the same way that they respond over here.
That
why
was
is there
my
an equal
follow-up
and opposite?
question.
Yeah.
Okay.
And go ahead, Amanda.
No,
Sorry.
go.
I would say, well, doesn't the way you measure it affect how the results as well?
In fact, it does. In fact, the measurement is the key to it. Okay. If you don't measure it, do they change? See?
Right.
Yeah. But when you do measure it and assign a value to it, you know what the other ones is automatically. And it'll be opposite. So that is strange, isn't it?
Sense. Yes.
It's almost as strange as, having to go to a break in a few seconds, right?
Oh, I was gonna say it's almost as strange as Mark being on top of things for once. Well, in the break department. Then again, that's not fair. He's covering everything else. The least I can do is
I think that's great, and I do believe we're at that time.
We are. So now everyone can have about 3 minutes to stop their brains from spinning after what you just said, and we'll regroup and meet back.
And when we come back, we'll talk about stellar evolution and what's going to happen to the sun after it evolves. See you guys. Be back in.
Hey members, the new KGRA DB app is now available on iOS and Android devices. Gain on-demand access to any KGRA DB programming. Download any show directly to your mobile device to listen or watch on the go. Go to the App Store and search KGRA DB.
Are we alone in the universe? The most important question facing humanity is on the verge of being settled once and for all. The Mutual UFO Network has been at the forefront of this journey for nearly 50 years. Our members worldwide are dedicated to the research, documentation, and awareness that will shape the future of humanity. Won't you join us?
It's not just a donation.
It's a warm blanket.
It's a bottle of clean water.
It's a roof and a bed.
It's knowing someone cares.
It's feeling safe.
It's a today that's better than yesterday.
Every dollar you can spare helps so much more than you can imagine. Please, donate now to help people affected by Hurricane Ian. Your support is urgently needed.
You're listening to the KGRA Digital Broadcasting Network. We provide unparalleled coverage of trending news in the world of ufology, cryptozoology, and paranormal phenomenon. Whether you're watching our video live stream or listening to one of our audio programs, you are getting the best from world-renowned researchers and hosts, guiding you through topics the mainstream won't touch. Miss one of your favorite programs? No problem. Head over to the members area at kgradb.com for access to our massive library of award-winning content. Make contact, stay connected, only at kgradb.com.
Hello and welcome back to SkyTube Radio. I want to say again, hello to Tara Dailis, who is here, and of course Amanda down there. Hey there.
Hello.
So before we move forward, I want to ask Amanda if there was any questions that are out there in the chat that might be worth answering before we move forward.
I don't recall any offhand, but you heard the man chat. I'm watching both the KGRA DB and Sky Tour Radio with Mark D'Antonio, both on YouTube. We're also on Facebook. So if anyone has any questions.
Yeah, Facebook, Twitter.
Any of the things we've discussed, anything that maybe you just had in the back of your mind for the next live show or anything else?
Okay, very cool. So anyway, we take for granted when we look outside during the day and we see the sun up in the sky. We take advantage of the fact that the heat from the sun keeps us warm. Even in the winter, if you imagine, I used to do a class for people called "What If the Sun Went Out," and it takes you through the next couple of days, 7 days or so, of what would happen to the Earth if the sun went out. And the first thing you would notice, of course, is that it would get dark, and all the street lights would go on, and you would notice that it's nighttime, even though the sky still has a weird residual blue glow because it takes some time for the atoms in the atmosphere to stop doing what they do. Okay, and so you'll see some glows that eventually fade in just a couple of seconds, but the sun would then have been sending us solar flux. So what would happen is that stream would continue for 8 minutes, all right, after the sun went out. And the flux would continue for another day or so or two, because that's actually protons and electrons, particles that don't travel near the speed of light, but at some velocity. So we might see some auroras for the next couple of days. And then after that, we'll never see an aurora again. Because of the fact that the energetic solar fluxes, the solar wind actually is what it's called, won't be coming here anymore. And then the next thing that will happen is that the temperature, of course, will begin to drop. And there will not be any more daytime and nighttime. It's just going to be nighttime. And the temperature will begin to drop, and it will get down. By the end of the first day, the temperature will probably have dropped like 20 degrees. And then if I recall, by the end of the third day, even the fourth day, the atmosphere is raining out of the atmosphere like snow. So carbon dioxide is falling as snow, carbon dioxide flakes, ice, raining out as snow. And the atmosphere getting thinner, it'd be getting harder to breathe. The oxygen, of course, would not freeze out of the atmosphere at that point. It would take a little while longer. Meanwhile, the oceans would be getting frozen over, and we would end up moving very quickly into basically a snowball Earth situation, where the entire planet would be frozen. Even in the Arctic to the temperate zones, it would be frozen. And the Arctic zones and the lower and higher latitudes would suffer the worst first, and the equatorial band would suffer last and be, of course, you get an extra day or two. And I'm paraphrasing this whole thing, but bottom line is when the atmosphere starts to rain out and we get the rest of the atmosphere raining out because there's no heating to keep it elevated in the atmosphere, then we would find that the end of the human race would come, and it takes something like 6 days without the sun, maybe 7, which is kind of interesting because you could last about 6 or 7 days without water. So 6 or 7 days without the sun.
Well, that's convenient then.
Yeah. You don't have to change your math.
Yes.
Speaking of that, we do have a few questions coming in from chat now, and I think this one's very topical. Our good friend Genghis asks, in the future, could we make a sun?
That's a very interesting question. Not
following on the back of what you just said, we might need to.
Yeah, I mean, probably not, but I mean, that we won't ever have to make one. But let's consider that. This is part of the stellar evolution thing that we're going to be talking about here shortly. But consider this: in order to make a sun, you need to initiate hydrogen fusion, the fusion reaction, and in short, that's hydrogen being made into helium. And to do that, you need to have something that's 13 million Kelvin, all right, in order to get going initially.
There's that word again.
That's that word again.
It's pretty warm.
Right? 13 million of the Kelvin. Now you can see that that's pretty high, all right?
It's not listed there.
It isn't listed. It's well out scale. We went to the boiling point of water.
Wow.
And that's when hydrogen can fuse into helium. The problem we have is that we don't have a vessel that can hold a sustained reaction like that, because the temperature and the energies would be so high that the vessel couldn't handle it. So what do? We have to figure out something. We have to have materials that won't melt and won't be changed, chemically altered irrevocably by this high temperature. We don't have that yet. So making a sun is, I think, the equivalent of making a fusion reactor. And they're working on it. And you know what they always say? It's only 10 years away. I've heard that every 10 years for the last 40 years. Go ahead.
Okay, I might be confusing things here, but the Large Hadron Collider?
Yes.
Are they not trying to reproduce like a Big Bang kind of thing?
They're colliding particles in order to see the types of results we get, right, from these collisions.
How do we know we'll be able to, in case that reaction, should any reaction happen? Like,
what do you mean, like something bad?
No, like if we could. I see. This is the problem. I don't have the right words, so it's really hard to explain. Like
you explain, I'll try and put it into words.
You were just saying, like, if we could heat something up hot enough, like for the hydrogen to helium or hydrogen to helium, whatever.
Yeah.
We wouldn't have a vessel to hold it.
Yes.
Now, what happens if the Large Hadron Collider is successful? How do we know whatever vessel we're using right now will be able to hold whatever it is that is created? I don't have the words.
No, that's fair.
Well, that makes sense, Amanda.
Yeah, because the Large Hadron Collider is not doing things at the energies required to create fusion. Okay, it's actually not trying to make a sustained fusion reaction. It's taking streams of particles and colliding them with each other to see what happens when they break apart. And the trails they make are very telltale and tell us certain things about what type of particle it is, what it's doing, why is it spinning. We'll figure that out based on the characteristics of the particle. But they're moving at a very fast rate, and that's why the ring is so big, to accelerate them to very, very fast speeds. Well, those particles are never being accelerated, for instance, to the speed of light, okay? Because they're particles, they're physical particles. They can never get to the speed of light, but they're going a percentage of it, for sure. And when they collide, they actually create these resultant splashes, effectively, that are examined. That tells us a lot about atomic structure and particles within particles.
But if you're smashing them together to see what happens, that almost implies you don't know what's going to happen, and that's why you're doing it. So what if the reaction or the interaction creates something like 13 million Kelvin? Then what happens?
Yeah, I get you. Well, the thing about that is that you can't create something Energy can't be created or destroyed. So you're not going to be able to create something with more energy than you put in, unless we consider that we're trying to create a fusion reaction, because we know that when you slam two atoms together of hydrogen, you get a certain amount of energy back, and we want more energy back than we put in to make that all happen. And we're very far from that right now. So in the future, if we do get more energy back than we put in, we're only doing it at a small level. We're doing it with only not a fusion fuel worth of particles. We're doing it with a small number of particles. So we're never going to get to that point. Many times in these collisions, if heat is generated, and it is, okay, well, it's only momentary. And a vessel can handle momentary temperatures. It can't handle constant temperatures. It can't handle temperatures that are always millions of degrees, for instance. It can't. So if it can handle a few thousand degrees of temperature, it can do it for a short period of time. And that's why the fusion processes that have happened so far have been successful, but they're not able to sustain because the vessel can't hold it, number one, and because they can't get the energy into the system fast enough to make the next fusion occur. So we're a long way from having to consider what your problem is indicating. But if we ever...
I know they're very, very over the top kind of hypothetical examples,
no,
but
that's fine, though.
It's just like, what if when we get there, we smash them fast enough that they is there any possibility they will start sustaining their own energy, like the after effects will, and just keep going? And that's what I'm wondering, but I don't have the right words for it.
No, I see what you're saying. You're actually, that was pretty well stated, though. Is it possible that the collision could create an ongoing reaction that sustains?
Yes. See, this is why I wish I knew the right terms, because that's exactly what I was trying to say. That's exactly. Okay. Because if we don't know, then we don't know. And once it happens, now we're in cleanup mode, not, if we can't, I don't know, prepare for it in advance, what happens when it happens, Yeah,
no.
That's the worrier in me.
No, that's fair enough. I get you. But no, the bottom line is that, if we collide particles, theoretically, we know what's going to happen. We understand the energies that are binding these particles together. We understand what's going to happen when they're unbound. We understand what's going to happen when they collide. If we don't know something, it's something inside the particle that we're looking for. For instance, I say we collectively because I'm not a quantum guy. I mean, I'm not a quantum physicist. I'm an astronomer. Two different things. Okay, but the truth is that the particles. Okay, I'll give you an example. The proton, right? A hydrogen atom has a proton in it, and it has an electron that's in this cloud going around it. It's everywhere at once, so to speak. The probability of it being in any one place is, pretty good. Okay, so the proton itself is made up of several other particles, and those particles are called quarks. Right?
I remember them up and down, and
it's right, exactly so. So for the proton, there's 3 quarks in there, and we discover those quarks via these types of processes by colliding particles and seeing, wow, hey, there's something inside these protons. Holy cow! Well, in collisions of other materials so far, they don't seem to have found anything beyond the quark. So the quark is the smallest elementary particle that we could see to this point. Are there more? Maybe. But now we're also talking about smaller energies. Okay. So if anything, we're going to be looking at reactions that are going farther and farther and farther down the low end of the spectrum, with less energies being developed, coming out. So we're going to have to be able to detect anything that might be happening through a new set of instrumentation we don't yet have,
Wow.
So, but I think that your question is good,
Again, every once in a while I'll hear something and then my mind just goes racing in a million different directions, and it's very frustrating not knowing the right terminology because,
Yeah.
Like even talking about like Earth's movement, like rotations and revolutions, like, they're similar, but that's a huge difference. So I need to know, I need the proper wording, but okay.
Yeah. Well, keep in mind that, the whole idea is that fusion is a very difficult process to achieve. And to do it in a sustained manner is even more difficult. And there's getting it to happen once, we can do that. Getting it to happen more than once, we can kind of almost do that. Getting it to happen in a sustained way, we can't do yet. Now, there are other issues. There's something called the break-even point, where you actually get out more energy than you put in, because the speed at which you accelerate particles, that takes energy to make them get that fast. And when they collide, if they give out more energy than you put in, you win. But so far, there haven't been any real successes there. So the bottom line is that as we look at what's coming forward, what's coming to the forefront, I should say, we're going to end up finding that we're going to be closer to fusion, and someday fusion reactors are all we're going to need to generate certain types of particles that might take us all over the universe. And it just takes a fusion reactor to do it. If several quantum physicists and aeronautical engineers are correct in their design, it goes to that thing I was lecturing about all over the country, which is how a possible unidentified flying object might actually work within the realm of physics. But that's not tonight's show. It'll be next week's.
Maybe next week's.
Yeah. Well, you won't be here next week, but that's okay.
I'll be here next week. Sorry.
So
we do have more questions from the chat. I'm just going back some here. Michael wants to know, have we practiced for the communication delay to Mars? Some people were talking in here earlier just during the break. Some people were saying there was going to be a 20-minute delay. Some people saying maybe 11. Do we know?
Yeah, it depends. It depends where Mars is relative to the Earth. Okay, so if we're on the same side of the sun, as Mars, we might have only a 4-minute time frame. Okay, but it could be as much as 22 minutes when Mars and the Earth are on opposite sides of the sun. And the Earth is going around the sun faster than Mars. Mars is going around. And every time the Earth approaches it, as we get closer and closer, it goes from 22 minutes to down to 11 to 10 to 9 to then 4 minutes and then back up again. So the time is going to constantly change, and it changes every day, depending on where Mars is relative to the Earth. Okay. So have we practiced, Michael? By the way, hi, Michael. Good to see you. Have we practiced for the communication delay? Yes, we have. With every rover we have there, we have the same problem. And we have the most active rovers and systems on Mars of any other nation. So, we have the Mars Insight lander. We have the Curiosity rover, which is still going as it has been since, I think, 2012. We have the Perseverance rover with the helicopter Ingenuity still going. And so we are practicing, and we do send out messages. I will tell you about one thing I had happen that I was watching some of the data feeds coming in from Curiosity, and Curiosity used the rock abrasion tool. It was spinning and making some marks and basically drilling down into a rock, and it separated this rock on a strata level, like when the strata comes apart. And when it did that, for all the world, I saw a fossil, and I quickly called a friend of mine and said, "There's a fossil. There's a fossil. It looks like a crinoid. A crinoid's an ancient plant from the early prehistoric seas." And they said, "Oh no, it's too late because of the time delay that we're talking about, as Michael's referring to. we had already sent it the message to continue drilling. So between here and Mars was that message going out, keep drilling, get rid of that fossil. It wasn't intentional. Because of the time delay, though, sometimes we don't get to see what we want to see, and sometimes we ruin something we should have.
Too bad you couldn't have taken like a screenshot or something, at least, the next time we're passing by. Not like it's going to be anytime soon, but like, go back, try to get back to that area roughly and go slowly, have some new equipment for the mission. I don't know.
Well, we do. And Perseverance rover has got a significant amount of improvements there. One of the things the Perseverance rover did, which is extremely, in fact, not the most important thing, is it demonstrated that it was actually very doable to take the carbon dioxide atmosphere, which is 98% of Mars' atmosphere, and turn it into breathable oxygen.
Mm-hmm.
Okay, and it was a
very cool
car battery size thing called the MOXIE, the Mars Oxygen In Situ Experiment. And it basically took the carbon dioxide atmosphere in, and it chemically altered it, did some work on it, and it spat out O2, breathable diatomic oxygen. But it also spat out a little bit of carbon monoxide, which is CO. Okay, well, the CO is bad, right? But the O2 is, of course, good. And they said, well, this is great because we can now manufacture rocket fuel. And that's true. But you can also set up a domed habitat that has these car size or small building size MOXIE generators that are processing the CO2 atmosphere of Mars day and night to make breathable oxygen in that dome for colonists.
Cool.
That's what I've been saying for decades. I'm like, can't we just make, like, for lack of a better word, like put a bunch of greenhouses up on like a moon or a planet or something and try to, if we can get enough, maybe with the blanket, maybe we could make an atmosphere.
Yeah. So now Uberku has an interesting question. Okay, I'm going to put up here. Uberku says, could the communication time from Mars and Earth be reduced if there were repeaters or relays in space between?
Interesting.
An interesting thought. You think about it, okay, but keep in mind that there is a terminal velocity. There's a speed limit in the universe, and the speed limit is light speed, and it's light speed that we're talking about here. So sending a direct signal from Earth to Mars is going to be faster than sending it to a repeater, having a repeater process it and send it out again. Unfortunately, the repeaters won't make things happen faster. They'll actually slow it down. You see why?
I don't know what a repeater is, but what about a relay, like all the Starlinks?
Yeah, I understand, but still, the direct
there's
path,
too many speed bumps in the road, kind of going here, then here, then here, then here.
Actually, that's a good way to think about it. Okay, but the speed bumps are not going to; these things are not going to buy you anything because the speed of light is constant in the vacuum in space. So when something reaches a repeater, at best, if it repeats it immediately and sends it out again, okay. And then the next one repeats it and immediately sends it out again. It's still going to get there at just about the same time, if not slightly less time, slightly more time rather, than the direct signal would, because you're processing the signal in a piece of electronics and sending it out. So there'll be some fractions, maybe nanoseconds, maybe milliseconds, that it's going to take longer for it to be processed by any electronics and resent. And you're not buying anything because you're already going at the fastest speed there is. That's a hard thing, right? Yeah. People don't realize it takes up to 22 minutes for light to go from here to Mars, because light is what radio waves are. You send radio signals and it takes 22 minutes, right? The electromagnetic spectrum contains radio waves, contains visible light, infrared, ultraviolet, all the colors we can see with our eyes, and that's all moving at the speed of light when you see it. And it's hard for people to think and understand that it takes a full 8 minutes for the light to get here from our sun, right? It takes 8 minutes for that to happen. That's pretty cool.
That's crazy. We still have other questions from the chat, but we haven't heard from Tara in a while.
I think Mark, weren't you going to talk though about stellar evolution? I'm
keep saying I'm going to.
That. So why don't you do that? That's what I'd like to hear about.
Okay, well, we have about a half hour here, a little over.
Yeah.
We're not doing a bottom of the hour break here, so we're just going to go right through until the end. So, bottom line is this, okay? When stars are created, right? Stars gravitationally condense out of basically a nebula. The solar nebula that we had here was a nebula that basically had a lot of a mixture of elements that were made in other stars, created by supernovas, okay, and also that were just there from the beginning of time. Now, remember this guy here. This is the periodic table, right? If you look at all the yellow elements in there, the ones that have yellow in them, these are elements that are made in supernovae, okay? If you look at the purple ones, those are elements that are made in merging neutron stars, all right? And the gray ones are the ones that are made in what are called type 1a supernovae explosions, where you have a white dwarf orbiting a red giant star, and the red giant leaks onto the white dwarf. The white dwarf is overloaded with gas to the point where it reaches a critical mass and it will explode. All right, that's a type 1a supernova. Well, you see, these particular elements were created in this way. So there's a whole slurry of these things available in the interstellar medium. So every nebula, or a nebula that's going to, say, make planets and stars, is going to have a bunch of these there, right? Have a bunch of this material. So we had a certain composition of materials when our sun was made. And those materials consisted of, well, many of the things we see in the periodic table. All right. And when we look at the sun spectrum, we see them in the sun spectrum. They're called the Fraunhofer spectrum. Now, those objects, those chemical elements, those elements in the sun are there because the sun was made with them. All right. It was made with them. The sun became a star with all these elements in its outer atmosphere. The outer atmosphere isn't doing hydrogen fusion that we've been talking about. Only the very core in the middle has been doing it. All right. So here's an example. Okay. This is the sun. If you look at that thing in the middle, that round thing in the core, that's where fusion is actually taking place. It's not taking place in the orange area. That's actually a radiative zone where the energy is radiating out from the core and coming up. And then near the surface, we end up getting like the boiling pot. We get a convection layer, which is the yellow layer in the sun, right? And that is a convected area. That's a convection current going in there. So material from down below in this radiative zone is boiled up to the surface and then back down. And that creates things like solar granules, a little texture that we see on the surface of the sun. And it creates sunspots, which are solar storms on the sun. So we see how the star is built. And our sun has this radiative zone around the core, but it's only the core where fusion's taking place. All the other material that we talk about that are in the periodic table that it was made with are in that major envelope. So in the orange part and in the yellow part, okay, that you see here, that's where all those elements are. And there's some in the core as well. But it's not hot enough for those in the core to actually do fusion, because to go from hydrogen fusion to helium, you need that 13 million Kelvin. To go from helium to carbon, you need over 100 million Kelvin. So the temperatures have to be exceedingly high. Now, a star like our sun can reach that, but it's not evolved to the point where it can yet. So it's interesting when we talk about how stars actually work. Once they're burning, they're called normal hydrogen burning. When we say burning, we really mean fusing, but many people use the word burning, okay? But it's fusion. So normal hydrogen fusion or burning is when hydrogen is made into helium. And in terms of what's really being made into what, it's an isotope. A variation of hydrogen is made into a variation of helium. But don't worry about that. Now, when the helium is made, the sun cannot do anything with it. So it sort of accumulates in the core. So the core of our star has a lot of helium ash, if you will, the burned remnants of the hydrogen to helium fusion process. Okay. And that helium in the core is just building up. Now, what happens is it actually begins to, the core itself is hot, but it's not hot enough for anything to happen with the helium. So it just sits there. Effectively, it's inert. Now, a star is always fighting gravity against the radiative pressure pushing out. Remember, in this image of the sun, okay, you have the core, and then you see that radiative zone. Well, that radiative zone, the darker orange part there in the middle, that dark radiative zone is pushing out with radiation, and the star's gravity is trying to pull it in. And there was a question in the chat earlier, what holds stars together? It's the star's gravity that holds it together. And as the star is trying to collapse, the radiative zone is pushing out with just enough energy to keep it inflated, to keep it at that right level. And that's called hydrostatic equilibrium. Don't worry about the term, but it's an equilibrium, right? It's pushing out at the same rate as trying to be crushed. So that's very important. Okay. So that's how stars live. And that location that they live like that, and where they always live at that point, is what we call the main sequence. So here you see the main sequence. All right. It's right here. You see that snaky line that's going down through the middle, and you see that there is it's like a snaky line that goes down from the bright blue, the upper left, down to the lower right, to tiny little reds. And then you see stuff above and below. All right. Well, that middle line that they all seem to cluster on was discovered by Ejnar Hertzsprung and Henry Norris Russell. And that is the main sequence.
And what are those letters at the bottom stand for?
I'm just about to get to that because I want you to do it.
I remember those letters.
You remember that? Yeah.
It's a long time.
We define stars by their color and their temperature, and the color relates to the temperature. Now, you see the letters along the bottom, all right? And I will let Amanda tell you what they are and what they mean.
Well, there's a wonderful mnemonic, and it's helped me over the years. At the bottom, you can see OBAFGKM. And if you remember the sentence, "Oh, be a fine guy, kiss me," or "Oh, be a fine girl, kiss me," depending on your preference. And yeah, the blue are the largest and hottest and bluest. And then the M's are the small, cooler red ones. And another thing that I liked from years ago, you always think like, red is hot and blue is cold. But if you actually look at a lighter, the hottest part is the blue at the very bottom. And then as it gets out and it cools, it turns kind of more orangey. Yeah. And I mean, these M stars are still like insanely hot. Don't get me wrong. They're not cold. They're not ice, but as compared to the O stars. And what are we, a G2?
G2, exactly right. See, got it. Keep in mind, folks, Amanda didn't know any astronomy until we started doing SkyTour Livestream, and she was a regular on SkyTour Livestream with us. Over time, she has absorbed quite a lot. And then when we did SkyTour Radio, she absorbed even more. So it was really quite amazing, how much she's absorbed. So I'm very proud of her. Now,
you're a great teacher.
Well, as far as things you said that aren't exactly correct, I'm okay with that because you've got the whole right idea. Okay, the blue ones are the most massive, and the red ones are the least massive, and the blue ones are the hottest, and the red ones are the coolest.
I should have said massive, not largest, not smallest. Yeah,
that's fine. That's fine.
That's not size.
Yeah. Yep. Because the most massive, our star can be bigger than an O star in terms of diameter. It depends on its state and evolution. All right. Kind of weird, huh? Because O stars are very massive, but an O star in the main sequence, all right, is one that's going to just be doing hydrogen into helium. And that means the star is going to have, a core, a radiative envelope, and then that's going to go out, possible convective envelope outside, like the boiling pot. All right. But when the hydrogen runs out, that's when things change. Because as the hydrogen begins to run out, that means that the star is now going to lose the battle with gravity, and the star is going to start to contract. Now, when the star contracts a little bit, that core is getting a lot of pressure on it, gravitational contraction pressure pushing on it. So the temperature goes way, way up when the hydrogen starts to run out. When that happens, the stellar wind pushing outward is increased thousands of fold, and that pushes out on those layers. And it actually causes the star to blow in size. And the star's outer envelope begins to grow and grow and grow. And that puts it in a whole new place in evolution, and that's called the red giant branch. It's where the star goes into a red giant. This will happen to our sun. When the hydrogen is exhausted in about 4 billion years, the sun is going to begin to collapse a little. As it collapses, it's going to get hotter in the core, all right? And then it's going to send out this stellar wind, which is going to start pushing the outer envelope out bigger and bigger and bigger, and it's going to grow. And by the time our sun reaches its maximum size after running out of hydrogen, okay, it's going to end up losing about a quarter of its mass. As it starts to do this, it's going to lose mass because of these huge stellar winds, all right? But it's also going to end up growing in size to the point where it's a larger and larger red giant is no longer going to be on that main sequence we talked about. It's going to be in a different place. And Robert Cruz says it huffs and puffs until it blows our planet down. Well, in fact, it probably could. But this is a diagram that I have. It's just a quickie. It's actually set right about on our sun, okay? Now you'll see the scale across the bottom is temperature, not color, but okay, it's right about for our sun, and the temperature, of course, is in Kelvin units, as you can see, and the luminosity is the intrinsic energy. You can see the 1 goes right across the page to that spot where this line, the second black line, is going up a little bit. Well, we run out of hydrogen, and the star will start to contract a little bit. As it contracts, as that corresponds to the track that's kind of going to the upper left, okay? As it starts to contract, it's getting hotter, so the temperature starts to increase a little, but it's also expanding. So its luminosity is also going up. So that's why it's going to the upper left a little bit. Then it starts to move horizontally over to the right a little bit. This is where the temperature starts to reduce. This is where the sun's size and diameter is getting bigger and bigger and bigger. We're approaching the red giant range now. That's where it's going to getting a red giant. You see my hands over here? Hi. Okay. It's approaching the red giant phase. And as it does so, it pretty much stays the same intrinsic energy output. So we still see it like that. Okay. But then it rapidly grows in size and ends up reaching that red giant, full red giant size. And that red giant size that we're seeing right there could actually take us out to about the orbit of Venus and maybe almost possibly a little further. So Mercury incinerated. Venus, it's already an incinerator, but it's going to be incinerated by this. Okay. So now the core in this star is still contracting. And now the core is going to contract and get hotter and hotter and hotter. Remember, we lost the hydrogen, okay? And it's now pushing out the envelope, okay, as it starts to get the hotter core, the stellar winds. So it pushes out that envelope being the outer parts of the star. And as that grows and grows, the core is contracting and contracting. And as it gets hotter and it reaches 100 million Kelvin, then something amazing happens. That's where all of a sudden, all of that helium in the core starts to fuse immediately. It's called the helium flash. Now, remember, the star is massive. Okay, the star is huge. So when the helium flash occurs, you'd never know it, because from the outside, you still see the big giant red giant star. You don't see any flash. You don't see anything. But in the core, the helium is now fusing at a very, very prodigious, rapid rate. And so once the helium flash occurs, several things happen in the core of the star. Okay. Remember, in the core, we think you want to say there might be atoms in the core, but there's only nuclei. There's only the nuclei of atoms in the core. And that's all we ever have in the envelope of the star, all the way down to the core. Unless it's really, really massive star, then we can have some atoms on the outside of the red giant, but not near the core. It's always just going to be these little protons and neutrons and electrons and so on, okay, that are in the core. And as that happens, the electrons, being completely separated from their atoms, are now being smushed together. And it causes a problem where the star tries to contract and it can't get beyond a certain level because the electrons are what are called degenerate. Remember we talked about that with white dwarfs in various times in SkyTour Livestream and in SkyTour Radio. Electron degeneracy is like, you have a checkerboard and you have one electron per square. You can't put any more in, all right? And you try to crush them and you can't crush them. Marbles in a jar is another analogy. You fill a jar with marbles, okay? Once the jar is full, you can't put a single other marble in there. And if each marble is an electron, that's an electron degeneracy. It can support a massive amount of weight pressing down on it, all right? Because they're as compressed as they can possibly be. And that's how electron degeneracy works in the heart of a star that is anywhere up to about 4 times the mass of our sun, right? So we're talking about a star that's slightly less than our sun to 4 times the mass. That's the range you're in right now. So once the helium flash occurs, well, then something else happens. If we look at the stars and where they are on the diagram, well, you see at the top right there, that yellow, that little bang symbol, that's the helium flash. And now the star starts fusing helium. And if you read the chart, you notice that it shows that the luminosity drops a little bit. And then, that's funny, new band name. Yeah, helium flash. Yeah. As the luminosity drops a little bit, you'll see that the star temperature is increasing. And so you'll notice that the red line there is now the horizontal branch. And that horizontal branch is the place where helium fusion is taking place. All right. That's where the star is converting helium into carbon and also oxygen on occasion. So that's where a star like our sun could end up making carbon and oxygen. Remember, I talked about carbon as a very special element in the periodic table. I've talked about it a lot. In fact, I'm a carbon bigot. I am highly prejudiced toward carbon, right? Tara knows.
Yes, you are.
Yeah.
No silicones here.
No silicon, right? Okay.
I'm waiting for a bad Austrian accent.
No bad Austrian accent.
The carbonator, no?
Yeah.
The carbonator.
Okay. Well, that's the terameter.
Sorry, I know it's brutal.
That's the terameter right there. That's the terameter.
Yeah. Mm-hmm. Oh, you were pointing at her. I thought she could do an accent, an Arnold accent.
Carbonator.
Yeah. No. It's true. I mean, I could do all kinds of, could do all, it's like, everybody down. Everybody get down. I'm the Terminator. Yeah.
Carbonator.
Oh, carbonator. Yeah. I'm the carbonator.
You're carbon and no one gets hurt.
I like carbon. It's all I know how to do.
Get my carbon back.
It's not a carbon.
It's not carbon. It's also oxygen as well. It has to be. So, oh gosh, imagine doing a whole show like that. So,
no.
The bottom line is that these carbon and oxygen atoms that are created are now the inert core in the middle. All right. So now when we talk about white dwarfs, remember we're getting there. Okay. We've talked about how white dwarfs many times are carbon and oxygen white dwarfs. Well, now you know why. Stars of a certain mass only ever create carbon and oxygen in their cores, and that gets highly compressed. And the surface of a white dwarf at the end is mostly carbon and oxygen nuclei. And so that's where this comes from. So when we talk about this, okay, many of these processes, the processes that occur later to fuse helium into carbon and all that, they're not as efficient because they're making bigger atoms. And so they're removing more particles from the system to fuse more things together. So it's so short-lived in a sense. The sun can go for 8 billion years before it might reach, say, the helium flash, and then helium flash is only going to go for a few million years, all right? Because the helium is going to be done in a very short amount of time relative to the overall age of the sun. Okay, so now the state of the star at this point is this, all right? It has a inert core of carbon and oxygen, as I mentioned, all right, because the helium and the horizontal branch is fusing. And I'll bring this up again. Come here, you. Okay, and in the red part of the branch there, the star is fusing helium into carbon and oxygen in the core, and there is a hydrogen shell outside the core, and within that is a helium shell now, a shell of helium burning. And as the star begins to run out of helium now, gravity wins out once again, and the star loses its equilibrium, and it begins to shrink again. And when it does that, the core begins to shrink again. And when that starts to happen, then the stellar wind is increased again from that core of carbon and oxygen, and the star begins to enlarge again. So it went to a red giant brand. It went to the red giant once, started to fuse helium, where it started to shrink down again, and then it comes back after running out of helium. It starts to go back up again and starts to increase in size and become a red giant for a second time. This happens with all stars like this. Okay, so you see a star become a red giant twice in its existence. So at this point, it'll have a fairly thick helium shell. It'll have a very thin hydrogen shell, and it'll have a carbon and oxygen core in the middle. And the stellar wind will be massive. And the thing at this point, this is where if Mars wasn't destroyed, which it probably wouldn't be by the previous episodes, now it probably will, because the massive stellar wind is going to send out particles. These particles are going to impact all the planets, and these particles are going to induce drag. And so if Earth didn't get pulled into this star, it would now. And when the Earth gets hit by these particles, it's going to slow down in its orbit and get tugged toward the sun and spiral into the sun, the death spiral. Not sure how many years we'd have, but it's pretty bad, So Mars might spiral in. Jupiter was going to spiral a little closer. And by this time, the luminosity of the sun will be 3,000 times what it was, and the radius will be 180 times what it was. So this is really, really an important stage. And so because the hydrogen and the helium are burning in these envelopes around the core, okay, you end up having instabilities in there, because they're subject to any of the other radiant processes going on. So sometimes those processes aren't as efficient, and you'll find that the sun will have these pulses, maybe every 100,000 years or so. And these pulses might be thermal pulses. And when that happens, the sun will pulse outward, and the star will expand rapidly. And then that stuff on the outside is going to keep going. It's going to keep right on going. And it'll be gone because we're going to have these strong stellar winds. And it's going to be about 100,000 years between the pulses. And it's going to do 4 to 7. That's kind of been what we've figured out. It does 4 to 7 of these thermal pulses. And when that happens, well, we have a degenerate core of this carbon and oxygen left over, and it's what we call a white dwarf. And the winds can move out at 600 kilometers per second from a white dwarf. So it's pretty crazy. So what's moving outward, though, is what we call a planetary nebula, right? Now, we've seen planetary nebulae before, and I don't actually have a picture of the planetary nebula. That was my failing. Okay. So that said, I guess we will not show that. But the planetary nebula that's formed is moving outward, and it's lit up because the white dwarf is itself very much not doing any fusion, but it's very, very hot. And that wind that I told you about at 600 kilometers per second has a lot of ultraviolet energy in it. And that ultraviolet energy is what would be cause the excitement of the nuclei out in that cloud of stuff leaving the surface and moving out into the interstellar medium. So that is in short what will happen to our sun. And I know for a fact, and I'm going to try this right now while I got you here. Let's go.
Oh, welcome to live radio, folks.
No, I got it. There we go.
Famous last words.
Yeah.
I got it.
I have it. Don't worry. I won't fall.
What are we expecting to see?
I'm going to show a planetary nebula.
Ooh.
Okay.
Cool.
There's a planetary nebula. Yeah, go ahead.
While you're looking, there was a question about nebulas, and I don't know if I can find it now. Oh, yeah. Alice was asking, are there any nebulas that we can see that's a binary star system where we can see the second star?
Oh, very interesting question.
Think offhand you could give her?
Binary star systems, true binary star systems, as opposed to double stars. Yeah, dozens. My mind is a blank right now. Alice, I will get back to you on this.
Okay, well, Alice, if you're not subscribed, please subscribe to both here Sunday nights on KGRA DB and as well as Sky Tour Radio with Mark D'Antonio, also here on YouTube and
Sky Tour live stream.
Live stream, sorry, we're on radio right now. It's been a long night. Oh, beautiful. Whose eye is that now?
That's actually the Helix Nebula. We took that in Sky Tour live stream. This was a 20-second exposure in our observatory telescope.
Amazing.
Yeah.
The eyeball looking at us.
That's right.
You showed another one. The first one you showed tonight with the dust clouds, and I was going to ask if you actually lightened that picture or if that's naturally how it came out.
The spaghetti?
Oh, you're talking about?
No, it was. It looked like a painting. It really looked like a painting.
This one here.
That one, yes. Did you lighten that up yourself, or is that how it came naturally?
Okay, both, because this is what it looks like naturally. Okay, and because of the limitations of the telescope, I had to coax this information out. But this is all there. So this is the brown dust. That brown dust you see, that's all the dust in the interstellar medium from which stars and planets will be made.
It's beautiful.
It is. That's called the Iris Nebula. That blue nebula at the top, there's a star there that is actually causing a lot of blue light to come off. Of course, has a lot of blue light in it. And there's dust around there that's just like this brown dust. The trouble is, or the beauty is, that dust is scattering the blue light from the star. So that's why we see it looking like this. It's really, really pretty.
It's unreal.
It's just beautiful. Yeah, it's just beautiful. And I'm gonna do one more thing here, because I want to show this, because I really.
We only have about a minute, 30 seconds left. Sorry for the distractions.
A minute and 30 seconds?
No, 30 seconds. 25.
30 seconds. Okay.
20.
Okay.
No pressure.
No pressure. Okay. Well, then I will just leave it at that. And
leave you on a cliffhanger.
No, it's not really a cliffhanger. So here's it. I'll just show you real fast. This is what we're talking about for a planetary nebula. That's what they look like. And you talk about zooming in.
Wow.
That blue thing is the white dwarf. It's hot and it's blue, just like Amanda told you before.
Mm-hmm.
That's right. Well, folks, you've done it again. You have wasted another 2 hours listening to Sky Tour Radio with myself, with Tara, and with Amanda, even further down there. Hello. So I want to thank you all for coming out here and spending time with us. Next week, we'll talk about possibly what happens with very high mass stars when they evolve. They evolve in a way that's extremely exciting and does some amazing things. We'll see. Lots of explosions.
And bring your questions back again next week. I do apologize. I know a ton came in that we didn't have time to get to, but we'll maybe start the next week's show with questions and.
Or we can talk about them in Sky through live stream when we stream. I don't think we can do it tonight. We got a front coming in out there, so we can't do it tonight, but we'll be there.
Subscribe and hit the bell for notifications because you never know when he'll go live.
Go to skytourlive.com when you get a chance too, and let us know what you think. All right. So thank you guys. And
just in case, Happy Christmas, Happy New Year, everybody.
And then there's that too. All right, guys. Have a good evening. See you later.
See ya.
Good night, Tara.